Thanks very much. It's really a pleasure to be here. I'm not actually going to talk directly about data assimilation today. I'm going to talk about the limits of predictability for weather, but there's a bit of a relationship, and I want to first acknowledge my colleague Tobias Zeltz. If you see an uncredited plot here, then that would be from him. Okay, so what I'm going to do today is I'm going to focus on predictability for medium range weather forecasting of sort of standard variables, pressure, temperature, things like this. This is in some sense the best understood weather prediction problem. And so it's something where we can really say something definitely about the limits of predictability. I'll mention other predictability problems briefly at the end, and of course we can discuss them in the question period afterwards. So there's three things that I'd like to do in this 45 minutes. The first one is I'd like to talk a bit about chaos and the butterfly effect. So why is there a limit on predictability? And this is worth doing because there's actually a common misunderstanding here that even a lot of people in meteorology get slightly wrong. Certainly I did up until a few years ago. Then I want to get to sort of the main result part of the talk. So error growth experiments. So what is the limit of predictability and how close are we to it? And for the last part of the talk, I thought it would be fun to see if I could put together some sort of rough estimate of how much room there is for predictability, for improving predictions before we hit the fundamental limit. And in particular, to try and partition it between how much can we get by improving the models, how much can we get by improving the data assimilation and the use of observations, and how much can we only get in the end by going out and observing more. So that's going to be a little bit crude and rough, but it's kind of an interesting exercise to go through. But let's start with the butterfly effect. So when people hear the term butterfly effect, they commonly think of this paper by Lorentz from 1963, Deterministic Non-Periodic Flow, because this was really the original paper for chaos. And what chaos means is sensitive dependence to the initial conditions. So that means small perturbations grow exponentially. Mathematically, you describe that as having a positive Lyapunov exponent. And this rapid exponential growth means that after a finite time, your errors will become as large as the variability of the system in total, and you really won't have any predictability anymore. However, this does not actually put a fundamental limit on how far into the future you can predict, because you can always push that limit farther off into the future by reducing the initial condition errors. And so here's an example of that. So this is some error growth. The blue curve here, so this is so an error kinetic energy measure. And what you can see, if you look at the blue line, is it increases in roughly a straight line as a function of lead time down here. And because this is a logarithmic axis, the straight line means exponential growth. And if you pick some kind of predictability limit, so if you predict some level of accuracy that you consider to be a useful forecast, you will hit that after a finite time. Now, if you make your initial conditions more accurate, then basically you shift the curve down. You grow again at the exponential rate, the same exponential rate, the lines are parallel, and you hit the saturation level, whatever you've chosen, later. So there's no fundamental limit on predictability here. It just depends on how good your forecasting system and your observations are. However, this diagram is actually based on a set of numerical experiments that I'll talk about later. And if you say, okay, well, now I want a really accurate forecast. So instead of increasing or decreasing my initial condition error by a factor of 10, I'm going to decrease it by a factor of 1,000, so the little green dot down here, then you can see something rather different happens. You get this very rapid initial error growth, and in the end, you hardly get any increase in the limit of predictability at all. And this is the weird thing about it, is what's going on in the atmosphere is actually something that's fundamentally different and in some sense worse than chaos. And this is actually what Lorentz had in mind when he talked about the butterfly effect, he wasn't thinking about his 1963 paper. He didn't use the butterfly effect until the late or the term butterfly or seagull, until the late 1960s. And that was associated with this paper. So predictability of flow possessing many scales of motion in 1969, because what Lorentz realized is that if you go to smaller and smaller spatial scales, the error growth rate is faster. So the exponential growth rate changes. The slope of the line gets steeper and steeper. And in fact, it looks like, at least, as you go down to the very smallest scales, it goes infinite. So we're not talking a positive Lyapunov exponent here. We're actually talking about Lyapunov exponents that go to infinity as the size of the initial perturbations goes to zero. And then, so that means that the small scales in the atmosphere will saturate really very, very quickly. And then what Lorentz discovered is that these saturated small scale errors will then grow upscale and contaminate successively larger scales through nonlinear interactions, with the end result that that predictability is lost for the entire flow. But because the error growth rate gets faster and faster as you go to smaller and smaller scales, there's a diminishing returns for making your initial conditions more accurate. And at some point, you hit a finite limit. Now, to understand this, it's worth having a look at the model that Lorentz actually introduced in this paper. So what he did was he started with the 2D turbulence equations, which are a reasonable first approximation for synoptic scale flows in the atmosphere. So he took the two-dimensional vorticity equation. You might recognize this. He wrote it in terms of a stream function and a Jacobian for the advection term. So basically, in this system, the vorticity of the two-dimensional flow is conserved. So it's only moved by advection. So Lorentz then constructed an error vorticity by imagining he had two solutions and subtracted them. And what you get there is the evolution of the error vorticity is then related by these nonlinear terms. It relates the error to the properties of the background flow, to sort of the average between the two different states. And Lorentz took this equation and through a couple of pages of rather hairy mathematics, he converted this into an equation for the error kinetic energy as a function of wave number k, so as a function of different scales, and found that they change through terms that involve triad interactions with two error scales plus a mean flow. So I certainly won't go into the details of the mathematical analysis, but there are two important things that Lorentz learned from this model. So the first thing that he learned is that the energy spectrum is critical. So if you look at the atmospheric energy spectrum, so here's a famous gauge and Nastrom picture that I expect everybody's familiar with, and it has two ranges. So on smaller scale, excuse me, on smaller scales from about 3 to 300 kilometers, you have a relatively flat spectrum of k to the minus 5/3. Whereas on larger scales, maybe 300 to 3000, you've got a steeper k to the minus 3 spectrum. Now, Lorentz in 1969 had never seen this picture. This only came along in the 1970s. Nobody actually knew what the spectrum of the atmosphere was. So Lorentz assumed minus 5/3, since that's what it is for 3D homogeneous turbulence in laboratories and so on. And if that's the case, then you see, in fact, this limited predictability. So here's a 5/3 energy spectrum. It's a straight line, because again, we're on a log-log plot. And if you introduce a spike of perturbation energy that saturates at the smallest scales, what you find is that it very rapidly grows upscale and saturates a larger range of scales. But you can see as time goes by, the growth rate slows down. So as you move to larger and larger scales, the growth rate gets slower and slower. But the important thing is if you go the other way, if you push your errors from, say, your initial errors from here down to smaller and smaller scales, you have to go further and further to get the same amount of increase. And you find when you do the calculation that there's a finite limit that you just can't get past. Interestingly, this is different for the k to the minus 3 spectrum, which is actually the energy spectrum of 2D turbulence, which again, Lorentz didn't know at the time. In that case, after an initial sort of very quick adjustment period, you can see you have an increase, you have a growth of the amplitude of the error that's actually independent of the length scale. You can see all the lines now are now parallel to each other, and they're constantly spaced in time, but this is a logarithmic axis, so constantly spaced in time means you've got exponential error growth. So this is actually more like the original 1963 paper, the one that sort of in the popular mind has now been given the name butterfly effect, even though Lorentz meant this sort of behavior. So you've got two types of behavior, and the really critical point is the energy spectrum. -3 is a transition. Any spectrum that's flatter, so any exponent that's smaller than 3 here, will give you limited predictability, whereas for -3, then you will have in principle, unlimited predictability, if you can make your initial conditions accurate enough. Okay, the second thing that you see from Lorentz's model is that the initial scale of the perturbations actually turns out to be unimportant. So to understand this, you need to actually look at the nature of these triad interactions in Lorentz's model, because there's two things that go on. So the first one is the one that you sometimes call the OR mechanism. So if you have an initial perturbation, so an initial error on a given scale, so look at the blue circle here, so that's a certain length scale. And if you have, if you have a feature in the flow, so not an error, but a feature in the flow on a certain scale, and if you have errors in the wind field, so your two trajectories of the atmosphere have a difference on the same scale or a very similar scale to this, that means the wind will be different across this scale. And that means that this feature will then be distorted and create some smaller scales and some larger scales. So there will be a constant interaction between scales. If you have an error on one scale, you will constantly spread that error out locally to other scales. But there's another process that goes on. Suppose now your error wind is now on a much larger scale than your feature. What this means is that the features in the two simulations will just be advected at different speeds. And that means that they will very quickly, because they're very small scales compared to the wind field, so even a relatively small error on the large scale wind will push these things completely off and completely decorrelate the small scales in a very short time. So you've got a slow upscale and downscale propagation of error, or relatively slow, but an extremely fast downscale movement. And this was shown really nicely by Duran and Gingrich. So they did an experiment where they took the -5/3 spectrum, they took Lorentz's model, and put in errors at the smallest scale and got the predictability, exactly as like I showed on the previous slide. But then they took the same error, so the same magnitude of error, but rather than putting it in on the smallest scale, they put it in on the largest scale. But that large scale error, even though it was tiny, so many orders of magnitude smaller than the actual wind speeds in the initial conditions, immediately scrambled the smallest scales, which grew to saturation very fast. And after a short period of time, you couldn't really tell the difference from having put in the errors on the small scale. And Dale Duran likes to describe this by saying butterflies are not important. The butterfly effect is important, but butterflies themselves are not. It doesn't matter what kind of initial error or what kind of perturbation or what kind of scale you put in. If you're in a situation where you have limited predictability, whatever the initial error is, it will immediately project onto the smallest scales, and the errors will grow upscale. So this is really how you get a fundamental limit. And I just wanted to mention something briefly. There's a lot on this slide, so I won't go through it all. But I only learned very recently that Lorenz's effect was or Lorenz's butterfly effect was essentially rediscovered about 30 years later by turbulence researchers. But it wasn't recognized as the same thing immediately because they were looking at particle trajectories in turbulent flows and discovering that these things were fundamentally unpredictable. So if you had two trajectories if you had two particles in a turbulent flow and they're kind of dispersing, if you took the limit of these particle trajectories getting closer and closer together, it did not bring the particles close together after a finite amount of time. After a couple of eddy turnover times, they'd be completely random again, no matter how close you started. And this is something that was actually discovered by Richardson looking at weather balloons back in 1926. And he developed this T cubed power law, this sort of anomalous diffusion equation for two particle diffusion. But recently people have realized that these are actually manifestations of the same phenomena. And connects up a few different things. So not only Lorenz's theory, Richardson's argument, but also questions like the singular limit of the Navier-Stokes equations as you let the diffusion go to zero. You know, if you take solutions of the Navier-Stokes equations for smaller and smaller diffusion, so higher and higher Reynolds number, you do not approach the solution of the Invisit-Euler equations. It's something else. And it's kind of interesting because one of the things that, at least philosophically, you always wonder about with Lorenz's butterfly effect is what happens if you go to really, really small scales. Well, at some point, you just hit the molecular diffusivity and everything gets smoothed out. So maybe at that point, this increase in the error growth rates doesn't happen anymore. And in fact, the flow is predictable. The problem is you'd have to have millimeter scale observations of everything. But it turns out even that isn't true because of course, the Navier-Stokes equations are just an approximation for flows of individual molecules. So not only do you have the sort of ensemble average of the molecular diffusion, you also have fluctuations about that average due to the molecular motions. And a paper came out, I guess it was about 2 months ago, which showed that even the random molecular motions or the random molecular fluctuations in a turbulent flow give you enough initial error to trigger the spontaneous stochasticity and lose the predictability of flow. So there's basically no way out. So I just thought this was interesting because there is in fact still quite a bit of research going on, not necessarily in directly in meteorology on this phenomena. Okay, so let's now just have a look. Okay, so how does Lorenz's model work when you actually apply it to a weather prediction model or a model that really intends to represent the atmosphere? And this was first, or this was done by Falco Yude, who used the MPAS model at NCAR, so global convection permitting experiments, and he did two forecasts with the model where he added temperature perturbations to one of them, just Gaussian random noise, with an amplitude of 1,000th of a Kelvin, so really, really tiny. And what he got was, if you look at the first 12 hours, so these are curves every hour, what you can see is, so the initial perturbations had a flat spectrum, okay, but you can see they grew most rapidly on small scales. So this vertical line shows where the numerical diffusion in the model starts to damp everything. And above that, you can see the -5/3 range, and up here, the -3 range in the background spectrum. But it basically grows the smallest resolved scales in the model very rapidly. But you also see this slowing down in the growth rate, which is pretty much exactly what Lorenz predicted for this -5/3 slope. On the other hand, if you go later in the simulations, so days 3 to 7, so these are now curves once a day, you can see this sort of up amplitude behavior where the lines are mostly parallel. It's a constant growth rate and it's independent of wavelength, which is what the Lorentz model would predict for a -3 spectrum. So in its basic result, the Lorentz model seems to be predicting the right sort of behavior. And so that's the sort of summary of the first part of the talk here, is there is a fundamental limit on predictability, which comes from the nature of the nonlinear interactions in fluid motions. And what it seems to mean in practice is that if you put in, excuse me, if you put in tiny perturbations, they will grow very rapidly on small scales, so basically up to about 300 kilometers in the -5/3 part of the spectrum. And these will saturate in 1 or 2 days. And after that, you will then have exponential error growth on the larger scales until they saturate, and that takes somewhere on the order of 2 weeks. So the question then is now, if we think about current weather prediction systems and so on, how close are we, in fact, to the intrinsic limit? And another thing that I think is worth looking at here is there's a lot of interest now in the new machine learning models. Can they reproduce the butterfly effect? And of course, the other question is, are current forecasts perhaps affected by the intrinsic limit? So I want to have a look at a couple of these points now. So how close is the limit? So here's a set of numerical experiments that Tobias Zeltz carried out. And what was done here was we took, in this case, the icon model, so global. You'll see in the end we had hundreds and hundreds of simulations. So we ran this at relatively coarse resolution, 40 kilometers, but we use a stochastic convection scheme, which is able to reproduce rapid small-scale error growth. So there's probably a talk in itself on the stochastic convection scheme, but that's the setup that we used. We took 12 cases, so basically one randomly chosen day per month through a year. And in each case, we then ran a 5-member ensemble. In the 5-member ensemble, we chose 5 members, again randomly, from the ECMWF ensemble data simulation system. So that gives us a sample of the initial condition uncertainty as it is currently. And then, of course, each member also had a different random seed for the convection scheme. So that was the basic setup. And by looking at the spread of this ensemble, we can get an idea of how the error growth is working with the current level of initial condition error. But then what we did was we then rescaled the perturbations of the initial ensemble around the mean. We shrunk the initial condition error to 50%. And then to 20% and 10%, and finally to 0.1%. So we decreased the initial condition error by a factor of 1,000, which should give us the butterfly effect. And when we did that, this is the behavior that we got. So this is now the energy spectrum. So again, the dark black curve is the background spectrum from the model. The blue curve, which you can just see at the bottom here, is the initial condition error with the current level of initial condition error. And what you can see is basically the error grows, the lines are all parallel. What we're seeing is the k to the -3 up amplitude error growth. And we're not really seeing any signs of the rapid butterfly effect growth at the current level of initial condition error. On the other hand, if we go to the other extreme and we take the initial condition errors down by a factor of 1,000, so now the blue curve has been shifted downward to here, then you see a very different behavior initially. You immediately see the very rapid growth at the smallest scale, so the peak moves to the smallest resolved scales. You see the errors grow rapidly, but it slows down with time, and then after a little while, you get back into this behavior. So we do, in fact, see the sort of butterfly effect behavior in these simulations based on real events, provided we make the initial condition error small enough. So how small is small enough? Well, let's back it off a bit. So if we go instead of 0.1% to 10% error, again, you can still see some rapid initial error growth and a shift to the smallest scales, but not very much. At 20%, you don't really see much at all anymore, and certainly at 50%, it isn't there. So the transition is somewhere in this range. And to make that a little bit clearer, what we did was we picked a saturation threshold, so how close we needed to be to consider predictability lost, and we plotted how long it takes to get to that saturation threshold, averaged over all scales. So what we picked was 50% of saturation. So that doesn't sound like very much, but that corresponds to an anomaly correlation coefficient of about 0.6. And ECMWF typically uses 0.8 as their threshold for a good forecast in the mid-latitude. So we're actually allowing a little bit poorer quality forecast than you might really want to have operationally. And so what you can see then is if you plot how long it takes the error energy spectrum to reach 50% of saturation, so this anomaly correlation, you can see with the butterfly effect, the 0.1%, the limit's somewhere around 13 days. So by this measure, and of course you can always choose slightly different measures or different levels of skill, but by this measure, it's about 13 days. On the other hand, if you go to the 100% experiment, so this is initial condition errors of the size that they are in the ECMWF system, then you see it's around 8.5 days. So that implies that our room for improvement here is something like 4 or 5 days for the mid-latitude forecasts. But to get that improvement, by improving the initial conditions, basically we need to get the initial condition errors down to about 10% of their current level. So on the one hand, there's some room for improvement. On the other hand, this suggests that it's going to be pretty difficult to get there. So there's still a lot of work involved in improving our initial conditions to the point where we can do that. Okay, so now let's think about AI models. Okay, so this was all these experiments were done with conventional NWP models. We also tried a similar experiment with some of the publicly available machine learning models. So if you look at this curve up in the corner here, this is now, again, difference kinetic energy as a function of lead time for, in this case, the first 3 days. The dark blue line here is the icon model, as we've used before, and you can see the initial condition errors increasing on a straight line, so the exponential error growth that you get on the large scales, which is what you expect. Okay, the colored lines here, red is Pangu weather, green is GraphCast, and the purplish color is ForecastNet. They do something kind of interesting. They actually damp the initial ensemble spreads, the initial perturbations, for about the first 12 hours or so, but they fairly rapidly settle onto an exponential error growth, which is the same growth rate as the conventional model. So it looks like after this adjustment phase, they're doing the same thing, and it's pretty easy to see what they're doing in the adjustment phase. So this is now the icon error energy spectrum. In this case, the gray line is the initial condition error, and you can see it growing and saturating and so on. Okay, if you look at any of the AI models, what you can see is they're actually very smooth. If you go to scales smaller than about 300 kilometers or so, the energy spectrum basically dies away. And that means when you put in the initial condition energy spectrum that comes from the ECMWF system, the first thing that happens is they immediately kill all the smallest scales. And then after that, the error grows pretty much the same as it does in the model. So that's the initial loss of energy. It's related to this smoothness of the smaller scales. And that already makes us a little bit nervous about how they're going to do on the fast upscale error growth for the butterfly effect. Okay, so here is now the 0.1% experiment. So this should be the butterfly. And what you see here is the dashed lines up at the top are the same lines as on the previous slide, but they're now squashed because we've extended the vertical axis all the way down here so that we can get the 0.1% initial condition error in there. And what you can see, if you look at the red and the purple curves, so this is Pangu and ForecastNet, they're actually giving you exactly the same curve as they did for the 100% experiment, but it's just shifted down. So they are producing the same k to the minus 3 chaos exponential growth, no fundamental limit predictability behavior, regardless of the initial condition amplitude. They're not seeing it at all. The green line here, I should say that the blue solid line here, this is an icon global convection permitting error growth experiment. And so you see the rapid error growth, the transition to the exponential growth, and then it runs parallel to the line. So this is sort of this would give us the 4 or 5 days of predictability, and then you don't get any more. Okay. If you look at the green line, this is GraphCast. It actually produces some rapid initial condition error growth, but it's weird. It saturates at a very low amplitude, still a few orders of magnitude smaller than where it should be. And you can see that also here on the energy spectrum. You get this rapid small scale error growth, but again, it saturates below the even very low amount of variability that this model has on small scales. And it turns out it's not really a physical effect at all. It's just some kind of noise. So this is the perturbation structure at 12 hours. And if you look at the ICON, global convection permitting experiments, you see very clearly that the initial error growth basically happens where it's raining. It's in areas of precipitation, so it's very patchy, it's very localized. Initially, it will spread out over time. Whereas GraphCast is a much broader scale. It picks up mainly the mid-latitudes again. It's very weak in the tropics, whereas it's quite the opposite for the more realistic model. So basically, the conclusion is that the AI models are not doing the butterfly effect. But does it matter? If we're really so far away from the intrinsic limits, so sure, maybe when we get our initial condition errors down to 1/10 of what they are. But in order to do, but it would be nice to check this. So in order to check this, what you'd really want to do is basically run a butterfly perturbation experiment every day as part of the operational forecast, and then see, do you ever get cases, maybe there's exceptionally rapid error growth or something, where the butterfly perturbation actually gives you similar error growth to what you get in current forecasts. Now, that's a bit of an academic exercise, and you'd never do it on purpose, but it turns out that ECMWF is currently doing this experiment by accident. So these are some figures that were provided by Linus Magnusson. So what happened was in the current cycle, they've brought the ensemble resolution down to what the high resolution deterministic forecast used to be. And that means that the control forecast of the ensemble and the high res forecast ought to be identical. But it turns out, for various technical reasons, that they're not perfectly identical. And in fact, there's some differences in the orography used in the two experiments, which turn out to be sort of on the order of a meter in orographic height. So, I mean, a meter's big for a butterfly, but you could imagine this as a flock of seagulls. It really is a tiny perturbation error. And if you so this has been running since the 1st of July. And so Linus produced this figure late last year. So just with the first 5 months of this, this is still running, but it's already been fixed in the new cycle, so it won't run much longer. And the gray lines show the RMS error, so for Z500, of the control forecast of the ensemble for each day through that period. And you can see here's the gray lines show you the typical error growth pattern. But Linus highlighted two particular events, so two periods that showed really very strong error growth And so in particular, these red curves, which correspond to a couple of forecasts at the end of August last year. And this is now the difference between the control forecast and the high res. So the ones that really differ by butterfly-sized perturbations. So normally, if you look at the gray curves, the error growth in this is much smaller than or sorry, the perturbation growth between these two forecasts is much smaller than the error growth of the forecast itself. But for one particular day, one particular forecast, in fact, the 0Z forecast for 28th of August, you can see that this butterfly perturbation has grown to comparable amplitudes to the forecast error. And the ECMWF ensemble is reasonably well calibrated. So the ensemble spread tends to be similar in magnitude here as well. So there seems to have been one case where the butterfly effect actually produces error growth similar to what was actually seen in the operational system. Just very quickly, for people who are interested in the meteorology, it was an interesting event. It was related to the extratropical transition of Tropical Cyclone Franklin. At 48 hours, you really couldn't see much difference at all, but very slight differences in the position of the cyclone amplified over time. And basically, in one forecast, you got a fairly strong extratropical transition. In the other forecast, you didn't. And this fed into a block formation over Europe, which ended up having really massive events. So it's kind of what a meteorologist would see as a classic low predictability event. So, but there's only been the one so far. So we've also looked at the next 6 months or so of the data set. Well, no, 5 months. I think that's all there is. And there hasn't been another one as dramatic as this. So it is possible that the butterfly effect is affecting current forecasts, but it's rare. Okay, let's now, okay, yeah. Summary of this part: practical limit 8.5 days. We can get 4 or 5 more days if we can reduce the initial condition errors by 90%. But this kind of event, and in extreme events, it's possible that the butterfly effect may matter, even with current levels of initial condition error, but it's rare. Okay, let's just now quickly look at the room for improvement. Okay, so here's the graph that I showed before, showing the intrinsic limit of about 13 days. Current initial condition errors give about 8.5 days. But this is a perfect model experiment. So we're just looking at error growth in an ensemble of simulations. Of course, the models have errors as well. And so we've added an extra point now, this green one down in the corner. This is the predictability time from the current ECMWF ensemble, so compared against observations. And you can see that's only about 7 days. And so that would be associated with the fact that the model itself is imperfect. So it's not just the initial condition error. So that suggests that there would be another 1 or 2 days, perhaps beyond this 13 days, or sorry, no, within this 13 days, which could be gained by perfecting the model. Now, but the problem with initial condition errors is, of course, that depends both on the observations and it depends on the data assimilation and how the observations used. I think I'll skip over this slide because of time and go right to here. So this is a graph from a really nice paper by Loïc Baer and colleagues at Météo France. And because one of the questions you would ask is, okay, so if we want to get an idea of how much the use of observations in the modeling system matters as compared to the coverage of the observational network itself, we really need to know how the observations are being used. And so you might think, okay, well, suppose I wanted to really do what these AI models would really have as their goal and do a purely data-driven weather prediction. So I just wanted to take some observational data and produce a forecast. How much observations do I need? Well, one thing we know is just taking a snapshot of the observations, or even a 12-hour window like we use in many data assimilation systems, is not enough. When we do data assimilation, we use a background state, and that background state is bringing forward information from old observations. So how old? Well, that basically is determined by the common gain matrix, because the common gain gives you the weighting factor of the innovations of the new observational information versus what's being carried in the background state. And you can estimate this from an ensemble of forecasts. And I say that's what the people at Meteo France have done. And so you can get an estimate of how the impact of old observational information decays with time as you cycle the system through. So when they did this, they get a line that looks like this. So this is 12-hour cycles on this. And this is a logarithmic axis. So the straight line here, again, means an exponential decay of information. And basically, it goes down to more or less nothing after 8 or 10 data assimilation cycles, or 4 or 5 days. So that means there's 4 or 5 days of data contributing to a current forecast. So is that a lot, or is that a little? Well, what's the maximum possibility? Well, the maximum would be the predictability time, because that's how far the atmosphere can remember initial information. So if you had a perfect NWP system, but imperfect observations, you would use all the information that was possible to use. So in other words, you would use 13 days of data, because that's as much as that's the maximum that the atmosphere would be able to carry forward, even in a perfect system. So in fact, this suggests that there's quite a bit of room for improvement. And the other way that you can see that is if you look at reforecast data sets. So this is just a plot out of the ERA 5 paper. If you look at the red line on here, so what this is this is predictability time in days. It goes from about 5.5 days in the early 2000s up to somewhere between 6.5 and 7. Now, this is by the ECMWF ACC 80% criteria, so the numbers are a little bit lower than the ones that we showed, because it's a stricter standard of forecast skill. But there's been a certain amount of improvement. And with the reforecast data in ERA 5, you can then say, okay, with a constant NWP system, how much improvement have I got just from improvements in the observational database? And so what you can see is that the operational skill, so the red line, has increased by a little bit more than a day over the period of this graph, so the 16 years. And the reforecast show about 25% of that improvement is due to the observation network. The rest implicitly is due to better data assimilation, better modeling system, because of course, if you improve the model error, improve biases and so on, data assimilation tends to get better as well. Interestingly, if you go back to ERA 40 and look at the equivalent number, it's about 15%, which suggests that, well, I mean, the 15% is actually a pretty shocking number. So over the period from 1980 up to can't remember, 2000, 2010, something like that, only 15% of the improvement in forecasts was coming from the observational network. Most of it was coming from the modeling system. That's tapered off slightly, but it's still mostly from the modeling system. So here's the summary of this last part. Okay, and maybe this is kind of the message of the talk. So the current practical limit of predictability is about 8.5 days by the measure that we showed. You can increase that by about 4 or 5 days by reducing the initial condition errors. If you perfect the model, you can maybe get another 1 or 2 days. And as much as 3/4 of the initial condition improvement can be obtained by better use of existing observations. So that's kind of good news for this meeting, because it means that if you think about where we are relative to the limit of predictability, data assimilation is probably the thing that's going to get us most of the way there. It's probably the most important thing to be doing. I said I would mention briefly other predictability problems, and for that I'll just refer to this very nice picture from Buitz and Leutbecher in 2015. So they were looking at predictability horizons. So they looked at the ECMWF systems, and they looked for the limit of detectable skill. So rather than choosing a sort of practical limit of forecasting like an anomaly correlation of 60% or 80%, they looked for when can you statistically distinguish the forecast distribution from the climatology. So this is really the limit of any measurable skill at all. And so if you look at the orange curve here, this is for upper level synoptic scale fields, the kind of thing that we've been focusing on in this talk. And you can see that they're getting numbers that are a little bit bigger than the ones that we have because they've chosen that, but it's the same order of magnitude. But basically, depending on what you look at, so if you start looking at average fields and things, you can potentially predict to much longer times. On the other hand, if you're looking at rainfall and extremes and so on, it's much shorter times. And there's only sort of 2 comments that I would make about this, is that first of all, these are kind of different prediction issues because the predictability very often depends on boundary conditions, interactions with the land surface, things like that. And so there's much more room for model imperfections and biases to be important here. So the sort of numbers and estimates that I've given don't necessarily apply. But on the other hand, it's very difficult to make estimates for these things because it's different processes and different parts of the modeling system that are influencing different things that you might want to predict. And the other thing that's worth mentioning here is that the skill levels for these things tend to be quite low in comparison to classic medium range weather prediction, the sort of levels of anomaly correlation that we're taking as saturated errors. By this standard, both these large scale and small scale things probably wouldn't show any measurable skill at all. Okay, so I'll just go back to this as my conclusion slide, and I'll be happy to take questions and comments. Thank you.
Thank you very much, George. This was an exciting presentation, very interesting. I learned several new things, which is always great. And I already saw several questions in the Yopad. I think I'll read the first one by Daisuke Hotta from Japan. He also thanks you for your presentation, which was very interesting and also educational, that's true. And the first question that he asked is, in your ensemble experiment, it seems that the upscale contamination from unresolved small scale is only represented by stochastic convective scheme. Does it mean that the estimated intrinsic predictability limit is controlled by the specification of the stochastic scheme? Can you comment on that?
So to a significant extent that's true, that the stochastic scheme is doing most of the small scale growth in those experiments. But the fact is, it doesn't matter much what you do on the small scales. This was one of the lessons from Lorenz's model initially, is you can put in the perturbations on kind of any scale and they all do the same thing. So since we did that set of experiments, we have repeated a limited number of them with global convection permitting experiments. So 2.2 kilometers, or I think it was. And so where we resolve the convective motions, and you get the same behavior, because basically anything you do on small scales, any way you represent it, boom, you're saturated within a day or two. And after that, the error growth proceeds in the standard way.
Okay, so this kind of answers the second question. So he also asked, what happens if you choose the initial perturbation amplitude to be completely zero? So I think...
Well, completely zero, then you're talking actual bitwise identical computer simulations, and they will be exactly the same. But the thing is, if he's thinking mathematically, so let's take the problem of the Navier-Stokes equations and you let the diffusion actually go to zero. Okay, what happens there is you lose the smoothness of the velocity field. And what it means is that limit, you lose the existence and uniqueness of the solutions. And in particular, you lose the uniqueness. So what it seems like with the Navier-Stokes equation, certainly with many of the shell models and turbulence, other models of turbulence that they use, the zero viscosity limit is actually non-unique. So there are multiple solutions of the equations that start from the same initial conditions in that limit. So mathematically, it really is non-unique. A computer, if you give it bitwise identical conditions, will produce bitwise identical simulations. But that's actually a problem of computers.
Okay. And then another question by Guokun Dai from the Fudan University. Does the lack of butterfly effect or rapid error growth in machine learning models come from the few inferences? For one-day forecast, dynamical models need more than 10,000 integrations, while LM models only need less than 10 inferences.
We really don't know what the problem is. I mean, my initial suspicion is that comes simply from the fact that these models tend to be smooth and they just damp all the scales smaller than about 300 kilometers. So rather than allowing any sort of rapid amplification, they're basically just killing everything on those small scales. And then the larger scales grow at the slower exponential growth rate, regardless of how small amplitude the errors are on those scales initially. So that's my suspicion, but this really hasn't been investigated in detail. But it's an important thing, because if it is just the small scales, then that would mean, of course, that newer models like GenCast that actually can produce an ensemble of simulations, essentially it can randomize parts of the simulation, might be able to do it. But we haven't had a chance to try that model yet, because I don't think it's been released yet.
Yeah, this was also a connected question that I had. So how does this affect the capability of machine learning models to produce a realistic ensemble that represents the uncertainty in the atmosphere? So if it's too small and they don't capture, I don't know, this rapid error growth in convective precipitating regions, it might not be a good ensemble that comes out of a machine learning application.
Yeah, and I think the answer is for larger scales and medium range things, I wouldn't worry too much at the moment. It would be very rare cases. And actually, if you look at like that one example that I gave, if you look at the skill of the operational systems, they were all terrible on that day. It was just really hard to predict in general. But yeah, but the thing is, if you start evaluating precipitation and so on, they haven't done very much of that yet. If you look at the papers, you'll often see precipitation is missing or only a few scores. They're just starting to work on that. So I think that's really an open question. The only thing that I would say is that basically any time that they've been given a clear challenge and a well-defined metric that they have to achieve, they've got there. So
it will be
it'll be
exciting
interesting
to see. Yeah. So I just checked the time, and I think in the interest of time, we have to move on. So I want to thank you again, George, and would kindly ask you if you could go to the Yopad and perhaps also answer some of the question just by writing your answers in the Yopad. And yeah, thanks again for the great presentation. It was a pleasure having you.
Okay, thank you.